Okay, now I'd like to show you an example where we can use the summing amplifier. So it's not just for a simple addition of signals, but you can use it to convert a digital signal to an analog signal. And this is what DAC means. So this is a digital to analog converter. Okay, so that means that your computer, for example, can provide a signal, but in order for your computer to provide a signal, it has first to digitize it. And the way it does that is by taking these four inputs, for example, and then sending signals to each of these inputs at specific times, depending on what kind of output signal you need. Let me explain further. Okay, so we have here this circuit. So this circuit is a summing amplifier, and as you can see, none of the resistances are equal to each other. So the input resistances are not the same, as well as the feedback resistance. Okay, and that's really specifically designed so that the output voltages have specific values. So let's solve for that first. Okay, so we begin by solving what currents through each of these inputs are. Okay, so we know that here, okay, this is grounded because of golden rule number 2. This non-inverting input is grounded, so which means this inverting input is also grounded, which means that the currents through each of these input terminals are defined by whatever voltage you have coming in divided by the input resistances. So if we have a voltage of 5 volts coming in for each of the terminals, for each of the inputs, okay, so for I naught, we have 5 volts divided by 200 kilo ohms, and this gives us 0.025 milliamperes. For I1, we have 5 volts divided by 100 kilo ohms, so that will give us 0.050 milliamperes. For I2, this gives us 5 volts over 50 kilo ohms, or this is equal to 0.1 milliampere, and for I3, this is equal to 5 volts divided by 25 kilo ohms, or 0.2 milliamperes. Now we can solve for the output voltages. If only output D0 is present, D1, D2, D3 are 0, then V output is equal to negative RF times I0, okay, which is equal to negative 10 kilo ohms, which is the feedback resistance, okay, times I0, which is 0.025 milliamperes. So this gives us a voltage of negative 0.25 volts. If, okay, so this is if D0, only D0 is given the 5 volt signal. Now, if only D1 is given the 5 volt signal, then we have negative RF times I1. So this is negative 10 kilo ohms times 0.050 milliamperes, or negative 0.50 volts. Again, if D1 is present. What if only D2 is fed the 5 volts? Then we have negative RF I2 equals negative 10 kilo ohms times 0.1 milliampere, or negative 1 volt. Okay, and finally, if only D2 is fed the 5 volt signal, then we have negative RF I3. Okay, the negative 10 kilo ohms times 0.2 milliamperes. Okay, negative 2 volts. Okay, and if D3 was the only. Okay. Okay, so that's how, or these will be the outputs if only individual inputs are given the 5 volt signals. Okay, so now let's take a look at this table, or this figure B. Okay, so in this figure, we have the terminals or the inputs D0, D1, D2, and D3. At specific times, these inputs have 0 values and also 5 volts values. For example, in this time 0, okay, in this time 0, all of them have 0 output. Okay, so since there's no input. Okay, now for time 1, okay, what we have here is that D0 is the only signal where the 5 volts, D0 is the only input with the 5 volts signal. Okay, so which means that the sum for this is just 0.25 volts. Okay, now for this one, the second one, okay, then we have D2. Okay, so I'll just write down here 0 volts, and then 1 is 0.25 volts, and then for 2, okay, we have only D1 present, okay, with the 5 volt signal. So which means that we have 0.5 volts for number 2. Now for number 3, okay, we have 2 inputs with 5 volt signal, and those are D1 and D0. So we add those 2 inputs together, so we have 0.75 volts as the output. For number 4, we have 0 for D0, 0 for D1, but 1 for D2. So now we're in 4. So 1 for D2, this gives us 1 volt. Okay, there should be negative signs here, but I didn't bother to write them. Okay, for number 5, we have D0 with 5 volts and D2 with 5 volts. So we have D0 plus D2, so that's 1.25 volts. So now you can see that the pattern is rising, right? So we expect that this is going to happen. It's going to happen like this. Okay, so 8 is 2 volts, 9 is 2.25 volts, 10 is 2.5 volts, 11 is 2.75 volts, 12 is 3 volts, 13 is 3.25 volts, 14 is 3.5 volts, and 15 is 3.75 volts. Okay, you can verify this for yourself. Okay, now how is this digital to analog converter? Well, this is your analog signal. Okay, so that's the output, okay, that you have here, and that goes to whatever circuit that you have, which needs this voltage. Digitization happens right here. Okay, now let's consider the time 0 first. So all of the inputs are 0. So if there's no signal, let's assign that to a 0 signal. But if there's a signal, then let's assign that to a 1. Okay. So for example, we have here D3, D2, D1, and D0. So for 1, we have all zeros, so 0, 0, 0, 0. Okay, now for number 1, for time number 1, we have all signals 0 except for D0. So this is 0, 0, 0, 1. For time 2, we have only D1, which is non-zero, so 0, 0, 1, 0. For time 3, we have both D1 and D0, so this is 0, 0, 1, 1. For time 4, we have D2, which is non-zero, 0, 1, 0, 0. For time 5, we have D2 and D1, 0, 1, 0, 1. Okay, so you can see that we can actually complete this, okay, and observe that if you're familiar, this is actually the binary form of these numbers. Okay, so each of this is a bit. So we have a 4-bit signal. Okay, so this is 1 bit, this is 2 bit, this is third bit, and this is the 4th bit. So we have a 4-bit, so to speak, computer here. Okay, so this is a 4-bit computer because it has 4 inputs. Those inputs can change from 0 and 1 depending if you feed a signal to it or not. Okay, so this is your digital signal and this is your analog output. So the summing amplifier converts the digital signal into an analog signal. Okay, so that's basically how it works. Okay, so if we graph that, okay, we will see the digital signal here, okay, and the analog signal here. And the way it converts is that, you simply add up or you scale the signals using the scaling or the summing amplifier. So you can actually produce a sinusoidal form, a sinusoidal signal, okay, or you can produce any type of signal. Well, here we have what looks like a triangle. Okay, so you can continue with this if you start to decrease the voltage in this manner. Okay, in the manner that is shown here. Okay, so or you can draw a sinusoidal voltage. So you have to select the proper bits to turn on and off at specific times. Okay, and so on and so forth. Okay, so basically that's how you use this summing amplifier as a digital to analog converter.